So now we're looking at complex numbers in trigonometric form. So recall, complex numbers in rectangular form are written in the form a plus bi, where a was equal to the real part and b was equal to the imaginary part of the complex number. So when you're graphing complex numbers, the y-axis is your imaginary axis. And the x-axis is the real axis. So if you were, for example, asked to plot, how about 2 minus 4i? So if I was to plot 2 minus 4i, I would go over positive direction in the real 2, and then I would go down 4 units. And I would get a point right in here. So sometimes in mathematics, it's easier to solve things in polar form. Sometimes it's easier to solve things in complex, rewriting them as complex numbers. And so here we're going to rewrite our complex numbers that were in rectangular form into polar form. And guess what we get to do? We get to create triangles again. And so let's just look at this and see if we can create this and rewrite this in polar form. And so if we look at this, we can create a right triangle. And we want to figure out what r is. I know that right here, my length is 2. And I know that my imaginary part, that length is 4. So I know that r squared is equal to 2 squared plus 4 squared. So r squared is equal to 4 plus 16. R squared is equal to 20. Taking the square root of both sides, I get r is square root of 20, which if I pull out the biggest square, that would be 2 root 5. I also need to know what theta is. Let's call it this theta sub r. I know theta sub r is in my fourth quadrant. So looking at this, let's use trigonometric functions that we know. So if we looked at tangent of theta sub r, this is equal to opposite, which is 4, all over hypotenuse. I'm not hypotenuse, opposite over adjacent, which is 2. So we're looking at tangent theta sub r is equal to 2. Okay, so we can figure out what theta is by taking the tangent inverse of both sides. I'm going to pull out the calculator. So making sure your calculator is in radians, looking at tangent inverse of 2, we get approximately 1.1. This, though, is in the fourth quadrant. So I know that theta sub r, well, theta is equal to 2 pi, right? Because I'm doing a full 2 pi minus my theta sub r. By doing that, I get 2 pi minus my answer and get approximately 5.1 or 5.2. Okay, so I know what my theta is. That would get me to where r is. So my theta right here is approximately that 5.2. So recall the x value of our point is our cosine theta. Well, x here, our r value we found was 2 root 2 cosine of 5.2. Y though in our case, that y is our imaginary number. It's like that y-axis is imaginary. So this is going to be RI sine theta. So our y value of this point is equal to r, which is 2 root 2 sine of 5.2.
It should be 2 root 5, ma'am.
Oh, thank you so much. Okay, so our form up here for our imaginary was a plus bi. Let's think of it, a plus bi. Let's just think about this. Our x value was our real part, so this is x plus. B was our y value, so yi. And so if I want to convert this into polar form, recall when we were looking at polar coordinates, our x value was equal to our cosine theta. Well, we found that our r value over here was 2 root 5. So let's put in 2 root 5 there. So we get x is equal to 2 root 5 cosine, but we found what theta was. Theta was 5.2. And recall that our y value was equal to r, which again is 2 root 5, but it was sine of our value, 5.2.
For I, do we put anything in there?
Yes, so because of this is x plus yi, we're going to rewrite this as, this is the same thing as x, which is 2 root 5 cosine of 5.2 plus yi. Usually we'll put the I out here so it's not after and you're not thinking it's part of the angle. So we can put I 2 root 5 and then the sine of 5.2. So technically, we just kind of did an example without me again giving you guys the rules. So let me give you the rules. So converting from rectangular coordinates for a complex number. So converting complex numbers from rectangular form to, it depends on your book, they're either going to call it polar form of complex numbers or trigonometric form of complex numbers. So something in the form of x plus iy, so a complex number. This can be rewritten as r times cosine theta plus I sine theta in your parentheses, or we can distribute that. Shorthand, you might hear this referred to r times cis. So that's cosine I sine theta. I'm probably just, well, I don't know what I'll do. Back from before, we know r is equal to the square root of x squared plus y squared by the Pythagorean theorem. We know that tangent theta is opposite y over adjacent, which is x. Or another way we can say that theta is equal to tangent inverse of y over x. Other things that we had seen, like I had put up there, x is equal to r cosine theta. And we saw that y was equal to r sine theta. So we should be able to take points in rectangular form of a complex number and rewrite it into trigonometric or polar form of a complex number. So let's look at a couple examples of that. So we have another example in front of us, 2 plus square root of 3i. The direction says plot each complex number in the complex plane and write it in polar form. So let's plot this in the complex plane. I think always plotting these is just really helpful because then you can see your triangle. So let's say that that's 2. Let's say up here is root 3. So real part is on the x-axis, go over 2. Imaginary is the y-axis, we're going to go up root 3. So I know my real part, again, 2. Imaginary part is root 3. And I can solve for r. That's the square root of 2 squared plus root 3 squared. So that r is equal to the square root of 4 plus 3, which equals the square root of 7. I need to know what theta is. I'm in the first quadrant, so I don't have to think about reference angles. I know that tangent theta is opposite, which is root 3, divided by the adjacent, which is 2. Too bad that wasn't cosine or sine, because we know what those values are. But we don't know that one for tangent. So theta is tangent inverse of root 3 over 2. So plug in that in the calculator. Tangent inverse. Make sure again you're in radians. square root of 3 divided by 2. So that gives us approximately 0.7. Actually, did I do something wrong? Okay, so theta is approximately 0.7. And so in trigonometric form, we get that R actually, that's not called R, that's called maybe Z. Z is equal to R, which is, sorry, root 7 all times cosine of theta 0.7 plus I sine theta. That's theta is 0.7. So I just want to show that if we did this, that we're going to get back approximately the same thing. If we plug that into the calculator, then we're going to get back what we got over here approximately, because we rounded 2 plus root 3I. And so let me just pull up Desmos real quick. So we plugged those values back into Desmos and we found that we got exactly what we had in the complex number in rectangular form. So now we're looking at another example, root 3 minus I. And so again, we want to plot this. So our real value is root 3. Let's go back. Actually, looking at the example in front of us, we have -1 plus I, and we want to plot this and we want to write this in polar form for a complex number. So our real part is -1. So we're going to go over to the left 1. And our imaginary part is I. So we're going to go up 1. And so we're over here in our second quadrant. So we have theta here, and we'll find theta later, but we're going to use a reference angle for now. Let's call it theta sub r. We can create our triangle, and we want to figure out what this length is in here. And again, we know r is equal to the square root of 1 squared plus 1 squared. So r is equal to root 2. So we want to figure out what theta is. We know that tangent of theta sub r, we'll talk about the angle in a minute, is equal to opposite. Opposite of that was 1, all over the adjacent, which is also 1. And so we're thinking about what angle of tangent gives us back 1. Well, the angle that would give us back 1 for tangent is pi force, or 45 degrees. And so I know theta. Well, if I went to the negative y-axis, that's pi. So I have pi minus my pi force. So my theta is really 4 pi force minus 1 pi force, which is 3 pi force. So our value of z in polar form is r all times cosine theta plus I sine theta. So we found r to be root 2. and all times cosine of 3 pi fourths plus I sine of 3 pi fourths. So we took our complex number in rectangular form and we rewrote it in terms of polar form. So going in the opposite direction, so we're given a complex number in polar form. So if we're given, let's say 3 cosine of 7 pi 6 plus I sine of 7 pi 6. So pretty much we're just evaluating these. So we have z is equal to 3 times, well, let's graph 7 pi 6. So pi plus a pi 6 is 7 pi 6. So we know our reference angle in here is pi 6. So we're evaluating our trig functions at pi 6. They're in the third quadrant, both sine and cosine are negative in that quadrant. So I'm going to have 3 negative cosine of pi 6 is the root 3 over 2. And then plus I, but we just said that sine is negative in that third quadrant, and sine of pi 6 is 1/2. So let's distribute our 3. So this gives me negative 3 root 3 over 2 minus 3 halves I. So sometimes doing operations is easier to do in polar form versus in rectangular form. And so if we were multiplying two complex numbers, so let's say z sub 1 is equal to, let's say, polar form r. Let's just do it this way, cosine a theta sub 1. Let's call this r sub 1. We're going to have two different values for a complex number. So let's say z sub 1 is equal to r sub 1 cosine theta sub 1 plus I r sub 1 sine theta sub 1. And let's say that z sub 2 was another complex number in polar form. And let's say it was r sub 2 cosine theta sub 2 plus I r sub 2 sine theta sub 2. So I'm trying to derive the formula that we would get if we multiplied our two trigonometric form polar forms complex numbers together. So z sub 1 times z sub 2. I don't really need the dot in between. So if we did that, we're looking at multiplying this out, r sub 1 cosine theta sub 1 plus I sine theta sub 1 all times r sub 2 cosine theta sub 2 plus I sine theta sub 2. Okay, so let's distribute that out and see what we get. And so if we distribute r sub 1 cosine theta sub 1 times r sub 2 cosine theta sub 2, we're going to get r sub 1, r sub 2 cosine theta sub 1 cosine theta sub 2. Let's distribute that to the second piece. And so we would here get plus, and I forgot, but it's okay. Let's go back in here and put r sub 2 in there. So that should have been I r sub 1, and this should have been I r sub 2. So now if we distributed that, we get r sub 1, r sub 2, cosine theta sub 1, sine theta sub 2, and I have my I in there, so I'm going to maybe just put this I out here. So now let's distribute the second term in the first parentheses. And so we would have plus r sub 1, r sub 2. Actually, no, we won't. We will have I, r sub 1, r sub 2, sine theta sub 1, cosine theta sub 2. Distributing over here, though, recall I squared is equal to -1. So I'm going to have I times I. So that's I squared, which is -1. R sub 1, R sub 2. Sine of theta sub 1, sine of theta sub 2. So I want to regroup these. I want to regroup these so I have the real parts together and I have the imaginary parts together. So notice that these two middle terms have the I in there. And these the first and the last term don't have the I in there. Notice that for the first and last term, they both have a R sub 1, R sub 2 in common. So I can technically factor out that R sub 1, R sub 2. That would give me here cosine theta sub 1, cosine theta sub 2. And then this piece right here that didn't have the imaginary, I have factored out the R sub 1, R sub 2. So this is minus sine of theta sub 1, sine of theta sub 2, plus, so for the middle terms, notice that we can factor out an I, but we can also factor out an R sub 1, R sub 2. So if we do that, now we have cosine, that should have been a theta sub 1. So cosine theta sub 1, sine theta sub 2, plus, I pulled out the I, R sub 1, R sub 2, so that's sine theta sub 1, cosine theta sub 2. So hopefully what's inside the parentheses, the first parentheses, looks like an identity familiar to you. Same thing. Hopefully that sum in the second parentheses also looks like an identity to you. So we have a cosine, cosine minus sine, sine. So I tended to say that a lot when we were in that section. So cosine, cosine minus sine, sine, that was the sum, actually in this case, yeah, it is the sum of our two angles for cosine. So it would be cosine theta sub 1 plus theta sub 2. Technically, notice that we have an R sub 1, R sub 2 on both of those. So I could technically factor that out. And then I would have plus I pulled out R sub 1, R sub 2. So now thinking about the identity that gave us cosine sine plus sine cosine, or sine, I would say sine cosine plus sine cosine. So hopefully you recognize that is the sum of two angles for sine. So this would be I sine theta sub 1 plus theta sub 2. So multiplying two complex numbers, here's our formula. So let's look at an example of using this. So now with the example in front of us, z is equal to 1 minus I, and w is equal to 1 minus root 3i. And we want to find z times w. And in here, the direction says, find z times w, write your answer in polar form. I think the easiest way to do this is let's first convert each one into polar form. So let's convert z and w into polar form. Okay, so I have 1 and a minus I. So that gets me down into the fourth quadrant. I know this is a length 1, this is a length 1. I know that my R value for z, this is equal to the square root of 1 squared plus 1 squared, which is square root of 2. Theta, well, my reference angle, I can see that it's going to be pi force, but I have technically tangent of my reference angle is 1 over 1. So we have pi force, but I'm in quadrant 4. So I need to look at 2 pi minus pi sub 4, pi force. So 8 pi force minus 1 pi force gives me 7 pi force. So I know my z value in polar form is r, which is root 2, all times cosine of 7 pi force plus I sine of 7 pi force. Okay, so now let's look at W. So W given was 1 minus root 3. So go over 1, down root 3. So we want to find R value for W. So R sub W is the square root of 1 squared plus root 3 squared. So square root of 1 plus 3, square root of 4 is 2. And now I need to figure out what my angle is. So tangent theta sub r is equal to the opposite, which was 1 all over, actually it's not the 1, it's root 3, all over the adjacent, which is 1. So that's not the one with all the 3's, and so I know that my reference angle is the 60 degrees or pi thirds. So I know that my theta value, though, is 2 pi minus pi thirds. So 6 pi thirds minus 1 pi thirds is 5 pi thirds. And this is for my theta sub w. So I know my w value is equal to r sub w, which is 2, all times cosine of my angle 5 pi thirds plus I sine of 5 pi thirds. So now I can use my formula to find z times w. So z times w, let's make my pen a little bigger. This is equal to, the formula said we're going to multiply our R values together. So I have root 2 times 2. I'm going to write it like this, 2 root 2. All times cosine. We're going to sum our angles. And so we had the 7 pi fourths plus the 5 pi thirds. Plus I sine of the sum of those angles. So 7 pi thirds sorry, 7 pi fourths plus 5 pi thirds. Okay, so now all we have to do, and we're almost done, is multiply or add our angles. So we have z times w is 2 root 2 cosine, getting a common denominator. So that would be 12. So this would be 21 pi. Actually, it's 12. So I'm going to multiply over 12. Multiply that first fraction by 3 over 3 and the second one by 4 over 4. So plus a 21 or 20 twelfths. Just getting a common denominator. That's going to get me a 31 pi twelfths. Plus I sine of 31 pi twelfths.
It should be 41 pi twelfths, ma'am.
41. Okay, you're right. So summing, we get 21 pi plus 20 pi is 40 pi twelfths. Plus I sine
41 pi twelfths.
I can't add. Thank you. 41 pi twelfths. 41 pi twelfths. Okay, I think I got that. There we go. So we've just multiplied two complex numbers and then put it in polar form. If we had done it the other way, so we could have technically looked at the rectangular form of z times w and then converted it into polar form, but I think that's a lot harder than how we just did it with using our formula. So in the next class period, we can look at another example of this, but we'll also look at dividing two complex numbers in polar form. We'll look at Drumwal's theorem, which is raising a complex number to an exponent, and look at examples of that. But that is pretty much all that we have time for today. So let's stop there.